Hello, FCCM. I'm Sen Ma, a PhD student from University of Arkansas under supervision of Dr. David Andrews. I'm pleased to show you our work and hope you will enjoy this video. First, let me ask you a question. How many of you are tired of waiting for synthesis when you design an accelerator in your FPGA? If you say, I'm fine for that, probably your design isn't big enough. If you are a hardware designer, then you may be used to have a coffee or enjoy a beer while waiting for FPGA catalysts to synthesize your design. But we want to get software programmers to join the game. Probably they are not as patient as you. So, in this video, we present a new approach called the Synthesis Free Accelerator, which allows software compilation and interpretation techniques to be used in place of synthesis for programmers to create accelerator in the FPGA. Here is an example to explain our design flow. Suppose the software programmer wants to create an accelerator for an inner product. It's easy to use a DSL to represent the functionality of inner product. There are two steps. First is doing vector modification based on two vectors, and then doing reduce. In the DSL expression, the vmod and the reduce are called functors. Based on what kind of functor you need, the compiler will link functors PR bitstring from a library. Then based on the data flow graph, the compiler will generate the virtual accelerator machine calls, which we name it VAM calls. These VAM calls can be interpreted and executed on a PR accelerator array during runtime, just like Java bytecodes. Let's look at the details of a PR accelerator array. Here is an example of an array with 3x3 tiles. Each tile is connected with a 2D nearest neighbor switch. The tile array will be configured during the runtime by the VAM calls generated from our DSL compiler. The PR bitstring for each functor will be loaded into a free tile during runtime. Well, let's start our demo. In this demo, we define the three vectors and we give initial value, and the accelerator we want to design is A times B. So next step, let's compile our DSL. To compile the DSL, we need three steps. First is SBT compile. And then use Delite C to compile the DSL. And next step is use Delite to run the code. Delite can help us to verify the accelerator we designed. Let's check the VAM calls generated by the compiler. So the file name is vamcall. So in this file is included the hthread source code, and the vamcall is embedded into this source code. The functor we use to create the accelerator is vmod. During the runtime, the vmod's PR bitstring will load it to the FPGA through the vamcalls. Let's run this code on FPGA. So first step, we have to compile the hthread source code. After you compile the source code, let's download it. It takes some time to download the ELF file to the FPGA since we include the PR bitstring. Okay, let's see the results. This code is running vector multiplication. The size is 5. And both software and hardware execution time is listed in the table. Since the size is 5, it's too small, so the hardware execution time cannot show up. So let's fix it and play around with the accelerator. So I can change the size to 4K, for example. And also this time I want to change my accelerator to do A times B times C. So since the size is too large, so I just comment out the print. This is my new accelerator to do A times B times C. So let's compile the DSL. So first let's do the SBT compile. And next step is Delite C. And next we can run in the Delite. Okay, we generate the VM calls and embed it into the hthreads source code. Let's compile the hthreads source code and download to the FPGA. It takes more time to download the EL file to the FPGA for this case, because we have two functor bitstream. Here we go. Here are the results. And this time the accelerator is A times B times C. And you can see this is the software execution time, and here this is our accelerator time. We just wait for software compilation time rather than the hardware synthesis, place and route process, which is almost forever. So if you don't believe me, okay, let's change another accelerator. I just changed the A times B times C to A times B plus C. So this tiny change, if you have to go through the whole hardware synthesis process, you know you have to wait for a long time. But for here, we just recompile the source code, and that's it. So let's run the same compilation flow. I think you have already remembered the command. So we do the delite C for the DSL, and then we use delite to run it. After that, we generate the VM calls and embed it into the hthread source code. And let's compile the hthread and download to the FPGA. Yeah, just a little wait for the download bitstream. I think you can bear the latency for download bitstream compared to the synthesis, right? Aha! You see the results? And this time is A times CB plus Z, and our execution time are different. And if you like, you can check the results to make sure I'm not lying. You see how easy and fast we can redesign the accelerator and run it on FPGA. Well, this is our demo. Let's go back to slides. This is the design flow I showed in the demo. The user application is written by the hthread programming model. We use Delite framework as the front end to compile the DSL. So how did we do as far as the programmer is concerned? The table shows productivity of our approach. Our compilation overhead is around 5 seconds, and here is our productivity improvement. At this point, you may ask, how much performance we lose by using our approach to design an accelerator? Good question. Let's see our preliminary results. We compare our approach with the software processor customer accelerator generated by Vivado HLS. In our investigation, we all feel comfortable saying about the performance is that these results don't invalidate our claims. Although these results show roughly equivalent performance, we don't want to imply that this will be the case for any accelerator. Our study is currently focused on productivity rather than performance. In the future, we will do a more comprehensive performance analysis of our approach. We fully anticipate that this level improvement of productivity will compromise with performance. That's all I want to show you today. If you like this video, please leave comments below or scan the QR code for more information. Thank you for watching.